speed. It's something we see every day. Cars racing down highways, planes soaring through the sky, and even our own planet, Earth, spinning at over 1,600 kilometers per hour at the equator. But what if I told you there might be something that defies everything we know about speed? Something that could travel faster than the speed of light? These mysterious entities are called tachyons, hypothetical particles that exist beyond the ultimate speed limit of the universe. Are they real? And if they are, what do they mean for our understanding of time, space, and reality itself? Let's unravel this fascinating concept together. Tachyons are a fascinating concept in physics, named after the Greek word tachys, which means swift. These hypothetical particles are said to defy the fundamental speed limit of the universe, the speed of light, approximately 300,000 kilometers per second. To understand tachyons, let's first consider how regular particles, like an electron or a car, behave. At low speeds, accelerating a particle is simple. It only requires a small push. But as the particle approaches the speed of light, something strange happens. Its mass increases. This means you need more and more energy to accelerate it. By the time you reach light speed, the particle's mass becomes infinite, and so does the energy required to move it. That's why, according to Einstein's theory of relativity, nothing with mass can reach or exceed the speed of light. Tachyons, however, flip this concept on its head. These particles aren't bound by the same rules. They don't start at sublight speeds and accelerate toward light speed. Instead, they're theorized to always exist beyond the speed of light. In fact, they can't slow down enough to reach light speed, just as ordinary particles can't speed up enough to reach it. It's as if tachyons exist in a realm entirely separate from our everyday experience of motion and speed. Here's where things get even stranger. Unlike normal particles, which require more energy to go faster, tachyons require less energy the faster they move. Imagine a car that speeds up as you take your foot off the gas. If you give a tachyon zero energy, it would theoretically move infinitely fast. This behavior is so counterintuitive that it challenges our basic understanding of physics. Tachyons are also theorized to have an imaginary mass. Not imaginary, as in fake, but imaginary in the mathematical sense. Their mass is described using complex numbers, which combine real numbers with the square root of -1. This makes tachyons a unique and purely theoretical concept because no known particle behaves this way. But what does it mean for something to always move faster than light? To understand this, we need to think about space-time, the fabric of the universe. In our normal experience, objects moving at different speeds follow a predictable flow of time. But tachyons would experience time in a completely alien way. Their superluminal speed might even allow them to violate causality, the principle that causes come before effects. For example, imagine you're playing a game of pool. You hit the cue ball and it rolls across the table to strike another ball. Cause and effect are clear. The cue ball strikes first and the other ball moves second. But if tachyons are involved, the effect might happen before the cause. In this strange world, the second ball might start moving before the cue ball ever hits it. This bizarre nature of tachyons has made them a hot topic in theoretical physics. They were first proposed in the 1960s by physicists Gerald Feinberg and others, who used them as a thought experiment to explore the boundaries of relativity and quantum mechanics. While no direct evidence for tachyons has ever been found, their theoretical existence helps scientists test the limits of our understanding of the universe. Tachyons are like a mirror reflecting the hidden possibilities of physics, a reminder that the universe might be far stranger and more complex than we can imagine. Why should we care about tachyons? Because their existence would fundamentally rewrite the rules of the universe. If tachyons exist, they could unlock new ways to understand the relationship between space and time. For example, tachyons could theoretically carry information backward in time. Imagine sending a message to the past. This has sparked intense debates about causality, the idea that every effect must have a cause. Could tachyons disrupt the natural flow of events? It's questions like these that make scientists both excited and cautious about the possibility of tachyons. Let's break this down with real-life comparisons. Imagine you're driving a car on a racetrack. At first, you're moving at normal speeds. Then, you hit the gas and go faster, let's say 200 kilometers per hour. Now imagine breaking the sound barrier at over 1,200 kilometers per hour. Tachyons would be like starting the race already faster than the speed of sound. But here's the twist. While a regular car would eventually run out of fuel, tachyons would get faster and faster as they used less energy. That's the mind-bending nature of these particles. On a larger scale, think of Earth spinning at 1,600 kilometers per hour and orbiting the Sun at 107,000 kilometers per hour. These speeds are mind-boggling, but they're nothing compared to the speed of light, nearly 300,000 kilometers per second. Tachyons, however, would be moving so fast they'd make light itself look slow. Tachyons emerge in some areas of theoretical physics, including quantum field theory and string theory. In string theory, for example, tachyons are associated with unstable states that suggest new possibilities for how the universe is structured. Physicists have also used tachyons as a thought experiment. Even if they don't exist in reality, their hypothetical properties help us explore the limits of relativity and quantum mechanics. These studies push the boundaries of what we know and pave the way for discoveries we can't yet imagine. Now, the question is, have we ever seen a tachyon? Not yet. Despite decades of searching, no experimental evidence has confirmed their existence. High-energy particle colliders, like the Large Hadron Collider, haven't detected anything that behaves like a tachyon. But the absence of evidence doesn't mean evidence of absence. Tachyons might exist in forms or places we can't yet observe. They might be hidden in the quantum realm or in dimensions beyond the three we experience. Until we develop new tools or theories, the mystery remains. If tachyons are real, they could revolutionize our understanding of the universe. Faster than light travel, once confined to science fiction, could become a reality. Imagine traveling to distant galaxies in the blink of an eye, or creating time machines that rewrite history. These ideas may sound fantastical, but they're grounded in the tantalizing possibilities that tachyons represent. They remind us that the universe is full of wonders waiting to be discovered. Tachyons are more than just a theoretical curiosity. They embody the spirit of scientific exploration, the desire to push beyond the boundaries of what we know and imagine what lies ahead. Whether or not we ever find tachyons, the search for them inspires new ideas, new experiments, and new ways of thinking about our universe. The universe is vast and full of mysteries. Tachyons remind us of the limitless possibilities that await discovery. What do you think? Are tachyons the key to unlocking the secrets of faster-than-light travel? Let us know in the comments, and don't forget to subscribe for more cosmic explorations.